Can share screen.
Great.
Here, you see that?
Okay, so in the way of introduction, for those who don't know, Lorenzo has a PhD from ICTP, as you have just heard. He has done a postdoc in Germany, in Bonn, and then he has done his second postdoc actually here. He was the first postdoc I ever hired, and I still regret that he is not closer near here. He is now full professor at UMass Amherst and has done really well and has done, very interesting things, especially recently. And he's going to give us some idea about what now interests him. All right, Lorenzo, the show's yours.
Well, thanks a lot. Thanks, Nemanja, for the invitation. I'm very happy to, well, I would be very happy to be there in person to enjoy the great food, I'm told. But I'm still, I'm very happy to be there also virtually. And thanks for the nice introduction, Nemanja. And, I spent 2 great years at Davis, and I always say that the only regret I have in all of my career is that I didn't negotiate for an extra year of postdoc before starting my faculty position. So this is a kind of multi-structure talk. The main results are based on this paper with Mike Roberts, who was a student who graduated from UMass about a year ago. But there are other papers that I'm going to quote. And in particular, the real motivation is from some oldish paper I wrote with Nemanja on natural chaotic inflation. So let me just go ahead, and I hope the talk will unfold in such a way that people follow more or less what's the story. And if you don't, please ask me questions. So let me start with motivation. I always like to start from this fact, the fact that, and this is a fact, there's many observations, they all concur to the same fact that, the structure we inhabit, so structure, galaxies, clusters, etc., originates from the growth of some small primordial spectrum of perturbations on the top of a homogeneous isotropic distribution of matter on especially flat slices. I didn't write that one there. And in particular, if one studies the spectrum of primordial perturbations, they satisfy a number of conditions. They're quasi-scale invariant, meaning that the spectral index defined to be equal to 1 for a scale invariant spectrum is about -1/30 at the 10% level, give or take. The spectral index, as far as we can observe, is constant. There's no running. Those perturbations are Gaussian in 1 part in 10 to 4, which is typical of what you consider free quantum mechanical fluctuations. And isocurvature modes that are below 5%. This really means essentially that all these perturbations, as far as we can tell, come from the decay of a single fluid. Even if, the universe is full now of different fluids, dark matter, neutrinos, baryons, they all come somehow from the decay of a single fluid. And the last thing that we are observing, or actually not observing, is the amplitude of gravitational waves. There's a dimensionless number that measures the amplitude of gravitational waves in the universe, and this number now is to be smaller than about 0.04, 0.036 at 2 sigmas, to be precise. And what is very impressive is that all these properties that are properties of the perturbations, plus a global property of the universe, that is the flatness of the spatial slices, are all in agreement with the simplest predictions of inflation. I like always to stress also the flatness of the spatial slices of the universe, because there's many alternative theories that usually try very hard to generate the properties, reproduce the properties of the perturbations, but usually often they have to assume as a given the flatness of the slices to start with. I will not make a review of inflation. I will just give the essential points that I will need to talk about, and I'm sure you've heard from many people, and I'm sure that Nemanja also talked a lot about it. So inflation, what we need for inflation is that the very early universe is filled by a scalar field phi, the inflaton, with a potential that is positive. And basically, at the very early stages, the inflaton phi is uniform or almost uniform in all of the universe, and it's far from the minimum of the potential. To give enough inflation, the potential V must be flat. What does flat mean? Well, it means that the derivatives of V with respect to phi must be flat, must be small in units of the Planck scale. Since inflation involves expansion of the universe, Planck scale is related to gravity, and that's basically the only other scale we are considering here. So, since people wrote down models of slow roll inflation in the early 80s, well, the idea of slow roll inflation in the early 80s, a zillion of models of V of phi have been written down in all possible ways with different motivations, etc. But it turns out that the simplest way of achieving, this kind of slow roll condition, so V prime much smaller than V divided by M Planck and V second much smaller than V divided by MP squared, is simply to assume that your potential is a monomial. If you have a monomial, of course, if phi is large enough, then all the derivatives become small compared to the potential itself. The most famous example, the textbook example of inflation is the quadratic potential of chaotic inflation by Linde. In particular, if one uses the amplitude of the primordial fluctuations generated during inflation, one discovers that the only parameter that appears in quadratic potential m is the mass of the inflaton that is of the order of 10 to 13 GeV. So this is beautiful. The other reason why I really like quadratic inflation, and this is really what got me into writing the paper I will talk about probably just in the last 10 minutes of the talk, is that there is what I consider a beautiful way of obtaining a model of quadratic inflation that is natural in the sense of technical naturalness. So what this is, as I said, not so recent anymore work with Nemanja and also with Albion Lawrence. The idea is the following. Suppose we consider a theory that contains a 4-form. A 4-form is a higher rank relative of the electromagnetic field that has the property that has as many indices, 4 in this field strength. By the way, you can see my mouse, right? Yeah, as the number of dimensions in space-time. As a consequence, because of the tensor structure, since this object is totally antisymmetric, the 4-form is proportional to the Levi-Civita tensor times a scalar function. And then if I write equations of motion in vacuum for the thing, I discover that this quantity Q must be a constant. And this is why usually in particle physics that's not so exciting, it's just trivial dynamics. There are no propagating degrees of freedom for this theory. What is the source of a 4-form is an object with 3 space-time dimensions, a membrane. The charge per unit of the surface of the membrane is denoted by E, and one can show that across a membrane, the quantity Q, that is this constant, actually makes a jump. So if I have a membrane, there's a Q that makes a jump, otherwise Q is a constant. Great. We will not actually care about membranes for the 5 minutes cartoonish presentation that I will give now. Basically, Q is constant and quantized in units of E. So what we considered is something that was actually considered in the past, and we applied it to inflation, was to mix a 4-form field with a pseudo-scalar, phi. And here, the theory that I'm writing down turns out to be the end of the story, other than this plus dots, dots, dots that I will discuss in a second what they are. The action of the theory, if I forget about the dots, 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 is actually invariant under shift symmetry. Phi goes to phi plus a constant. Of course, this is invariant. The phi, this term here, takes an extra term, but this extra term is a total divergence because f is a total derivative. So the action is invariant. And so because of this, if I assume that my initial theory has a shift symmetry, I am guaranteed that the shift symmetry is unchanged. In particular, no polynomials in phi will be generated. If one write down the equations of motion away from branes for this system by varying the action, well, these are the 2 equations of motion. The first one is as before, is a for divergence of something equal to 0. So I can integrate it. And I have an integration constant Q, that is a constant, again, away from membranes. And then I just plug this F into the second equation for phi. And what I discover is that this theory describes a scalar field with the mass mu. And the shift symmetry that I had there is still somehow there secretly, because I could replace Q to Q plus constant, phi goes to phi plus a constant, and the theory maintains the symmetry. But for any given Q, so in practice, once the vacuum is chosen, this theory describes a massive scalar. So again, this term here, this mixing with this parameter mu that turns out to have the dimensions of a mesh, is actually a mass term for my pseudoscalar. So this term, as I said, is a mass term. The theory is massive while the shift symmetry is completely unbroken. In particular, I guarantee that there are no other polynomial contributions to the potential. The symmetry is broken spontaneously when a solution is picked. And this last part, I really don't care. So this is, for me, a very nice reason to like quadratic models of inflation. And I'm done with the discussion of this quick model. As I said, this is mostly just for motivation. So how about data? Okay. So turns out that quadratic inflation is agreement with all the observations, all the observed properties of the power spectrum, including the scalar spectral index, but is ruled out by non-observational tensors. This is the paper from Bicep-Keck from last, what was it, October. And basically, this is the landscape for inflation. This is the scalar spectral index, and this is the tensor-to-scalar ratio, so the amount of gravitational waves. And you see in the Bicep-Keck, by not observing primordial gravitational waves, are confining the available parameter space to this blue bubble. The quadratic inflation predictions are this red line. So you see it's many, many, many sigmas away now. So this is very much ruled out, which is a pity because, as I said, everything else works just fine, including, surprisingly, or not, I don't know, including the spectral index. If I just go down vertically from any point here, I'm dead on my parameters. So this is, as I said, it's a pity because it's the simplest model of inflation, but it doesn't work just for one thing. These lines were computed assuming metric perturbations generated by the standard mechanism of amplification of vacuum fluctuation. Now the question is, can we salvage n squared phi squared? And in other words, let's see how robust the conclusion is. And I will use a lot of theorist prejudice, and you might like or dislike what I'm going to talk about. Feel free to dislike. I kind of like it, actually, in the end. But I should say, for full disclosure, that there are other ways of saving quadratic inflation, well, quadratic near the origin inflation, by, in particular, flattening the potential at very large values of the inflaton, which is a natural way, which is achieved in a natural way. But here I will consider something different. So let me introduce very quickly supersymmetry for inflation. What if supersymmetry, even if it's not observed at the TeV scale, kicks in? We are working at the 10 to 13 to 10 to 16, depending on what you measure as energy scales. So what if supersymmetry is valid there? If I just write a simple superpotential, phi squared, then this generates a potential phi squared, which works great for the generation of a quadratic potential for inflation. Let's forget for the time being that this is ruled out. And let's press ahead. Let's see what we can do if we put supersymmetry there. So if we have just global supersymmetry, this cannot be it. Because during inflation, the inflaton takes values larger than Planck scale, in which case we cannot use supersymmetry. We have to use the full supergravity. And of course, this generates a lot of problems that have been well known for, again, 30 years or so. This is the potential, scalar potential in a theory with a certain number of chiral superfield in supergravity. Now we have two objects that we can play with, the Keller potential and the superpotential. if I go back to the supersymmetric regime, I would have that, this is equivalent to sending mp squared to infinity. So this term goes away, this term goes away, and e to the k becomes 1. And I get back my supersymmetry potential, which is the part I liked. These new parts are all parts that I don't like, actually, because, for instance, as typically people consider, if you consider a polynomial Keller potential, this object here will dominate for large values of Planck of the inflaton, or this term here. This is one of the things that messes things up. And the other things that messes things up is the so-called Eta problem. That is, typically, the e to the k makes the potential very steep at large phi. There are ways out, and I will discuss some of those in what comes up. But as a general statement, these two terms, both the e to the k and the additional terms proportional to w, are a problem. Here, I'm not aiming as much at finding a model of inflation in supergravity that works, even if eventually this is what I will care about. What I will be aiming at is finding a model of inflation in supergravity that mimics quadratic inflation. And it turns out that these models have been developed from the early 2000s, and in particular around the 2010s, for the presence of these two extra terms proportional to w. These are typically solved in what are known as stabilizer models. Models where the superpotential depends actually on two fundamental, two chiral superfields, S and phi, and the superpotential is the form S times f of phi. Then, if I find a way, and in particular, I can usually find a way of doing this by using an appropriate chiral potential. If I find a way of setting S equal to 0, then W is equal to 0 during inflation, which means that both these terms here are not active anymore. And so the only term around is dw d phi, in particular dw ds. So I will assume that I am in this situation. I will not worry too much about constructing a full stabilizer model. There are stabilizer models that send S to 0 for a sufficiently large value of phi. So I will assume that the superpotential is the form S times f of phi, where f is some appropriate function. The other complication, as I said before, comes from this k, the Keller potential. This makes the potential V too steep at large values of phi. This is the Eta problem. And this is usually solved in models that are shift symmetric. In particular, for instance, in models where the Keller is function of phi plus phi star, then the imaginary part of phi will not appear in this exponential and will not make the potential very steep. And I'm happy to use these shift symmetric models also because this was the same kind of model I was dealing with my 4-form, even if my 4-form example, as I said, serves me more as motivation than as actual working model. Here I'm working with a regular model with chiral superfields. Okay, so I'm trying now to obtain quadratic model of inflation in supergravity. The theory is more complicated. There are more degrees of freedom. In particular, there are fermions, there are new interactions, and one can ask whether there is some new phenomenology and whether this new phenomenology can be useful to save my quadratic inflation. And of course, I wouldn't be giving this talk if the answer were no. So, part 2. Any questions so far? This was just introductory, really. No. Okay. So this is now let's forget about this specific model. Okay. Let's just talk about fermions during axion inflation. This is work based on a couple of papers with these guys, Peter Ashhead, Lauren Pierce, Marco Peloso, and Mike Roberts. What we consider was the following situation. Suppose that during inflation, I have a pseudoscalar shift symmetric inflaton. Again, this is very well motivated for a number of reasons. What phenomenology can we do with fermions? Usually, people don't study fermions during inflation for the obvious reason that fermions are Pauli blocked. And so they cannot have effects at large scales because the energy in long wavelength modes is very small. you can build up energy in long wavelength modes only if you have large occupation numbers, because the energy of each quantum is small because it's a long wavelength. There's also the extra complication that if I usually consider just a massive fermion, if the mass is too small, the fermion is not produced by the expansion of the universe because it's conformal. If it is too heavy, it's not produced because it's too heavy. And so there's not a lot of chances of producing a lot of fermions. Here I'm considering a different situation where the fermion that I call here Y is actually coupled to the pseudoscalar via this derivative coupling. This is a coupling. A here is the scale factor, m psi is a constant that is the mass of the fermion. And F is a coupling constant with the dimension of the mass that I can identify kind of with the F axion for my inflaton field phi. Okay. So this new term changes things. So one first interesting thing, clearly this term is shift symmetric. One thing one can do is a field definition this way, which allows to write the Fermi Lagrangian in this different way. And this is actually, in this way, it's not obvious that the theory is shift symmetric, while it was in the other way. But what is obvious here is physics becomes more transparent in this form, however. I observe two things. First, in the limit m psi goes to 0, the coupling with phi disappears. This because this transformation becomes a symmetry. Second, and this is what I care about, this field now, this fermion psi has effectively an oscillating mass. If phi is evolving linearly in time, phi dot equal to constant, then this is an oscillating mass that oscillates with amplitude m psi and frequency given by this number, phi dot over f, essentially. And so I can expect to have resonant production of fermions up to momenta of the order of this UV cutoff. And indeed, this is to show that we solve the equations. You can decompose the fermions, don't look at the details. The only thing I want you to look at is, if anything, that there are two dimensionless parameters that control the system. One is the mass of the inflaton in unit of the Hubble parameter. Here I'm assuming that phi dot is constant and the Hubble parameter is also constant. So I'm assuming that the mass of the fermion is constant. This ratio, mu tilde, is a constant. And also this parameter psi, that is a dimensionless measure of the velocity of the inflaton, is constant. And you might remember that this basically, well, psi times h is kind of the cutoff, the frequency, psi times h is the frequency at which the inflaton, the fermion mass is oscillating over time. So this is how many fermions I'm expecting to produce. And then one turns the crank, compute things, and I'm just going to show pictures because I think this is better. So first of all, to have a picture of what's going on, I have inflaton. The inflaton is rolling with a constant velocity. As it rolls, these fermions feel a time-dependent mass and feel a time-dependent background, which leads to resonant production of fermions. These fermions are produced, and at the same time as they are produced, they are diluted by the expansion of the universe. So you reach a steady state regime in which you have a constant occupation number of fermions as a function of time. And this is an example of the occupation number of fermions. So I notice a few things. In this left panel, in black, I'm plotting the number of, let's say, left-handed fermions, and in red, the number of right-handed fermions. So I observe that for the right-handed fermions, I'm only producing them with very small momenta, and then their occupation number drops down. On the other hand, for left-handed fermions, their occupation number stays kind of constant until up to momenta that are several values, several times the Hubble radius or the Hubble scale. So this means that I'm producing these fermions, and these fermions are kind of filling, they're not completely filling. You see the occupation number is about 10 to minus 1 in this example, but they're filling with a semi-constant occupation number the Fermi sphere up to momenta that are much larger than the Hubble radius, which means that I can get very large occupation number for these fermions. Of course, I have to be careful to make sure that I don't have back reaction effects that I cannot control, etc. But I can get relatively large occupation number for these fermions, not because I'm filling up to large momenta. Notice that the fermions I'm producing are only left-handed. If I want to play games like leptogenesis, for instance, this is a way of filling the universe with left-handed neutrinos only until the end of inflation. Also, the total number of fermions is proportional to the value of the parameter m psi. As I said, if m psi goes to 0, no fermions are produced. So you see the difference between the left plot and the right plot is that m psi is a factor of 10 smaller. And so you see in the right plot, you produce less fermions. Great. So you have this universe full of fermions. And this is a formula for the...
Sorry, can I ask a question?
Yes. Sure.
So I'm a little bit confused. You're saying the fermion is produced, but the universe is exponentially expanding.
Yes.
So if you want to achieve equilibrium, you are saying the fermion production is also exponentially produced?
Yes. If you compute the total number of fermions that have been produced on the whole history of inflation, it will be an exponentially large number of fermions.
Okay.
You produce them, and at the same time, they are diluted. So, and you have this steady state because I'm assuming, again, that I'm neglecting the back reaction on the evolution of the inflaton in the meanwhile. If I had to account for the back reaction, of course, the inflaton would slow down because it would lose some energy in producing those fermions.
Okay. So
okay.
The assumption that phi, the first derivative of phi is constant is essential, right?
Absolutely.
Okay.
But you know, if you can do a yes, but if I drop that assumption, I expect in a case things to behave qualitatively in the same way. Just the inflaton will slow down a little bit more. Actually, inflation will last a little bit longer.
Okay.
Let me just clarify a little bit. So basically, if I understand correctly, I'm not sure I do, but you're cranking up the gauge field first, and then from the gauge field you're discharging it into fermions, right?
No.
Okay.
In this case, actually, I'm directly producing the fermions
from the inflaton.
I'm saying from the inflaton using the dimension 5 operator.
Can you show it again?
Sure. Well, this one. Or if you prefer, this one.
Either way. So what I'm really asking is actually this. Let me.
Sure.
I think I sort of see it. Are you saying that one helicity of the fermion becomes tachyonic?
Is resonantly produced. The mass is evolving, oscillating like crazy.
But that's only at long wavelengths, right?
Well, it depends. It's at wavelengths comparable to the frequency at which the mass is oscillating.
But
it's really resonance.
So
yeah.
Just a second.
Yeah.
So it's the phi is oscillating, yes?
So phi is linear in time. So phi dot constant. So phi is proportional to time.
Right.
But then if I write a Lagrangian in these terms, then the mass depends on the cosine of phi. So that becomes the cosine of t. So it's really, you know, the dead pushing the swing at a constant pace.
Okay, I think I understand.
And if the swing is the light length,
like level crossing, you have this phi
absolutely
that's slowly rolling down, and it's basically just reshuffling this fermion spectrum completely. And then every once in a while, you go to the resonance where one of the fermion combinations is massless, and then you just dump a lot of this energy from phi. And of course, if you're ignoring the energy from phi being lost, then this just continues. As phi is scanning, you continue repeating this, and okay, I'm
I mean, to elaborate a little bit better, since it's coming up, and since there was a question of whether, you know, it's important that whether phi dot equal to constant is important, and as I can give up phi dot equal to constant as long as while phi dot in the time in which phi dot changes, I stay for long enough in the same resonance band. If I don't start changing like crazy, then I cannot stay in the same resonance band, and then there's nothing happening.
I don't want to interrupt you. I think it's curious, but I don't want to interrupt you. We can talk later, okay?
Yeah, sure. But, you know, I'm happy to discuss
I'm going to say one word. What I think all
Please.
of this has always been, but it hasn't been yet properly. This was related to the question I asked you earlier. I think this is all a form of Zitterbewegung. But okay, later.
Maybe, yeah. Okay. So, okay. So the thing is, but you know, from the point of view of dimensional analysis, let's put it just from the point of view of dimensional analysis, what's going on is just that now I have a new scale that is phi dot over f. And phi dot over f can be very large. And it's not the mass. So while pumping up the mass at some point just makes the mechanism not efficient because I don't have enough energy. Here I have this scale phi dot over f that on the other hand can be very large, but at the same time doesn't give me any Boltzmann suppression if you want. It's not the mass. So for instance, and this psi dot over f is basically this parameter psi. Once we do an inflation in units of the unit time, that is the Hubble parameter, is this parameter psi. And so you see, for instance, one thing on which we didn't do anything, but I think is kind of cute, is that here, for instance, I'm showing the occupation number for psi equal to 10 and this parameter mu tilde equal to 10. This means these are fermions that are 10 times more massive than a Hubble parameter, and still I'm producing a lot of those because of this pumping term that is pulling out a lot of energy. Okay, so what do we care about in this case? The universe is full of these fermions. These fermions were produced by the inflaton because they interact with the inflaton. So if they are around, sometimes they're going to infect the inflaton perturbations. Somehow I can have a phenomenon where, for instance, a fermion scatters off a quantum of inflaton and produces an inflaton. Or I can have, more specifically, processes where I have two fermions that fuse and produce one quantum of inflaton, a 2-to-1 process. Since I have a non-thermal but a bath of fermions, this is going to happen. And so one can ask the question whether all these inflaton fluctuations that are generated by the fermions turn into something that can become cosmological perturbations. And so we computed the contribution to the power spectrum of the scalar perturbations. Usually the scalar perturbations are produced from the amplification of the vacuum fluctuations of the inflaton, just because we are in a de Sitter space. And now I can have also a semi-classical, if you want, phenomenon in which I have these fermions around that scatter and produce quanta of inflaton. Okay, I can compute the power spectrum of the quanta of those quanta of inflatons. And we computed it in the informalism. Turns out it's, you know, you can have collaborators that like to compute integrals exactly, and then you can show off that the integral can compute it exactly. But what really matters is at the end, we get an extra contribution at the end of inflation to the power spectrum given by the process of fermions sourcing inflaton quanta. And this contribution is given by this formula where m psi is the mass. Well, you know what that parameter is. Psi, we said, is a parameter that is typically larger than 1. F is that F of the fermions. Great. And what is interesting is that this stuff, in principle, can be larger than the vacuum fluctuation. So you can have a source contribution that is larger than the other one. One can compute the spectral index of this contribution, and one gets this expression, whatever it is. It's not very important, just to show that we computed it. I mean, it will become important, but the details don't matter here. Okay, then we went ahead and please, Marcus.
Lorenzo,
Yeah.
sorry to interrupt. I'm sorry.
Please.
Can you remind me what xi is again? I'm sorry.
Okay, psi is, let me show you the formula. Here in the green is phi dot divided by 2fh. So if you want, is the frequency of the inflaton mass oscillations in units of the Hubble parameter. Sorry, is the frequency of the fermion mass oscillations in units of the Hubble parameter. Typically, you know, phi dot is square root of epsilon h Planck mass. So h cancels out. So this stuff goes as square root of epsilon m Planck divided by f. where epsilon is the slow roll. So if square root of epsilon is like 0.1, this stuff can easily be 10 if, you know, f is 10 to 16 GeV.
Okay, thank you.
And that's more or less the order of parameters I will think about later on when I will put actual numbers.
Okay, thanks.
No problem, my pleasure. Okay, so I will not elaborate on this. We spent a lot of time on non-Gaussianities because non-Gaussianity is actually one of the things that is constrained the most from observations. And in particular, with this phenomena where you're producing secondary perturbations, you worry about having non-Gaussianities because you have, you know, two Gaussian fields fusing to produce a new field, and the new field is non-Gaussian by itself, at least in first approximation, so you worry. So we spent a lot of time computing it, but the main result is, well, we have an expression for FNL. The main result is in this plot here. And here, this is, and the main result is that non-Gaussianities are actually small. We were very surprised to see that, but then we understood why. So let me guide you very quickly about this, around this plot, even if I will show another one later on that is basically the same one, but in different coordinates. So on the x-axis, you have this parameter psi. And on the y-axis, you have this dimensionless quantity m psi over f. The theory, in principle, has three parameters. We can always eliminate one by invoking that the power spectrum is given by, is in agreement with the observation. Power spectrum of perturbations is in agreement with the observations. And so we are left with turns out that we have only two-dimensional parameters. And basically what we found is that there is, well, top left is a region where we don't trust our perturbative calculation, but other than this, things might be okay. Top right, the red top right is ruled out because of back reaction. Here we would produce too many fermions, and this would drain out too much energy out of the inflaton. Bottom right is a regime, well, where the effective field theory is not valid. Remember, we are assuming that we are using a dimension 5 operator, and so the cutoff is about 4 pi f, and so in the top right, basically the relevant energies are above 4 pi f, and the white part is all allowed. And what we discovered is that there is this green line, and on the bottom left part is vacuum-dominated power spectrum, which means that the contribution to the power spectrum from the fermions is small and negligible. So the perturbations are the usual one from standard models of inflation. And the top right here is a regime where, on the other hand, the scalar perturbations are dominated by the fermions. So why is this interesting? Because in this case, you would have stuff that is in agreement with everything observed, but the spectral perturbations is not generated by vacuum fluctuations or perturbations. I will skip this one. It's not so important. This is the main result I have for this part too. That is that the system, usually when Planck measured the scalar perturbations, it measured really h to the 4 divided by phi dot squared. But here we have a regime where actually Planck measured this other quantity that is completely unrelated. And of course, this leaves some freedom with model building. So this is the main result here. Then one can ask the question about gravitational waves. We spent 1 year computing gravitational waves in this model, and it turns out that they are too small. So the spectrum of tensor perturbations is the same one as in the standard models of inflation. Basically, the fermions are not powerful enough to produce a lot of gravitational waves. Great. This is the end of part 2. Questions here. There was some, I don't know if I should elaborate a little bit more on the physics there. Again, the short version is the inflaton gives a time-dependent background to these fermions. Thanks to this dimension 5 operator, these fermions are produced resonantly. There's a lot of them around. They interact with the inflaton, and in particular, you can have phenomena where the two fermions fuse to produce an inflaton, and you can have a regime where actually this is the dominant source of cosmological perturbations. CMB is not coming from amplification of vacuum fluctuation, but it's coming from this fermion producing inflaton.
So can I ask you just one question?
Please.
Just out of curiosity, since you're here.
Sure.
When you showed this formula for producing for pumping the fermions, and it depended on this cost of this, there was some phase which was phi
Sure.
divided by t.
Yes.
To pump up your fermions to required levels where you want to get the scalar perturbations to be 10 to the minus 5 or so, how many full periods did this phi have to travel? Roughly.
A lot. A lot.
Okay.
Thousands per refolding.
Thousands per refolding.
Yes.
Okay. Okay. All right. Okay.
Hundreds, thousands per refolding. Lots.
Okay.
Yeah, yeah.
So in other words, you're basically, I think what you're doing here, you're taking the fermion vacuum and you're spinning it like crazy.
Exactly.
And it
I
is
think
the
that-
spinning of the fermion vacuum, which is, you know, through squeezing, producing these. Wow, curious. But okay, this is also a little bit worrisome, but that's fine, you know. It sounds very non-perturbative is what I'm saying.
Oh, it is. It is very non-perturbative. If I try to see this at perturbative level, I will not. I need to solve those equations exactly. And then, no, believe that if I do small perturbations of the exact solution, I get small perturbations of the result, which I think is correct. But if I try to expand this in powers of 1 over f, no way.
Yeah, yeah. Anyway, thank you.
Yeah. Okay, part 3, I managed to, I think, get back on time, more or less. Reviving chaotic inflation, I hope so. Okay, so what we did with Mike was to ask the question. In these models of supergravity, where we have these fermions, can we have a regime that where what I just discussed is realized? So to start with, we just performed a general analysis of the behavior of fermions in a cosmological background in a general n equal to 1 equal to d equal to 4 sugra with 2 chiral superfields S and phi, and with the stabilizer system. Okay, so superpotential is of the form S times f of phi, where f is an arbitrary analytic function of phi. And the Keller potential is of the form of a sum of a Keller potential of phi and this G of SS bar that is there just to realize the stabilizer mechanism. And really, other than this, we forgot about it. So the stabilizer condition is S equal to 0, which implies that W is equal to 0, which implies that the potential takes this very simple form for an arbitrary Keller potential. Okay, so it turns out that during my PhD thesis, I had to deal with a similar system because there were claims of overproduction of gravitinos at the end of inflation. And thankfully, there's this 80+ pages paper by Carlos Kaufman, Linde, and Van Proyen, where they give the general equations for a general number of chiral fermions in a general inflationary background. We specialize to the case of 2 fermions. So these are the equations from that paper. We have 2 matter fermions plus the gravitino. Gravitino has helicity 1/2 and helicity 3/2. Helicity 3/2 behaves very nicely, and I will forget about it, is gravitationally coupled, it's not really interesting. The helicity 1/2 part of the gravitino, so we have really 3 fermions, 2 matter fermions and the helicity 1/2 part of gravitino. But one of these fermions is actually the Goldstino. So we can set it to 0. And so we have a system with 2 spin 1/2, helicity 1/2 objects that are denoted by theta and upsilon. These are the equations from Carlos Kaufman and Van Proyen. They're terrible. Each of these quantities is defined in a different page of that paper. So that makes things even harder. This is, this was probably half of the work was to put together all the definitions in the same page. And eventually, this is when you have a good, great, devoted student. what Mike did was to able to perform a large number of field redefinitions to bring the system to a very simple one. So it turns out that the system with a number of field definitions can be brought to the form of two fermions that I called Chi1 and Chi2 with a diagonal mass matrix where that are in the same form actually. M1 and M2 are two reasonably complicated functions of the background fields. Of course, M2 multiplies gamma 5, which implies that in particular, if I'm dealing only with real fields, M2 must be equal to 0. Because if I'm dealing only with real fields, I don't have parity violation around. And again, I didn't even bother writing down the expression for M1 and M2. And so this was the general analysis we did. And then we said, okay, what can we do for our model? So let's consider a model. If I do just quadratic inflation, I'm screwed. I'm just going to keep quadratic inflation, nothing is going to happen. But let's consider what is kind of a natural thing. So let's consider this. Remember, let me go one step back, two steps back. My superpotential is the form W equal to S f of phi, and the potential is basically f of phi squared. So we specialize to f of phi that is of this form. A term mu phi, where mu is a constant, and this term basically gives just my quadratic potential for the inflaton, and a small instanton-like correction, proportional to some dimension full quantity lambda hat and e to the minus phi over f. Okay, square root of 2, etc. are just there to get good normalization. The scalar potential is the simplest scalar potential that respects shift symmetry that I can write down. And it's written this way so that the imaginary part of the inflaton, the imaginary part of phi is actually the inflaton. And to fix ideas, think that the parameter mu is over the 10 to 13 GeV. This parameter lambda hat is about 10 to 14, and this f scale is 10 to 15 GeV, give or take. So what happens? This f contributes to the, even in the global supersymmetry limit, this term here, proportional to lambda hat, will give a term proportional to cosine of phi. Remember, the imaginary part of phi is the inflaton. So we'll give a term proportional to cosine of phi and sine of phi to the mass of the fermion. So that was our guidance. More specifically, if I write down the full scalar potential for this theory, I have that the field phi as a real part that I call rho, and the imaginary part that I call phi, again, var phi, that is the actual inflaton. This is the full potential, long and ugly. But rho is very small, and in this case, I'm left with a potential that is what? Just quadratic here, plus small sinusoidal oscillations. Okay? And what I'm assuming is that the small wiggles are really negligible, because what I really care about is my quadratic inflaton. And for the fermions, it turns out that this M1 and M2 are very well approximated by a simple expression that is given by this expression. Mu, that is the same parameter that measures the mass of the inflaton, times this constant, whatever, times cosine of phi over f plus I sine phi over f times gamma 5. So the fermions get exactly the same form of cosine and sine contribution with gamma 5 that I was considering in part 2 of my system, that, if you remember, was given by this expression. Okay, so this is the result in this specific supergravity model that I remind you is given by a relatively simple superpotential, this. And this is the toy model that I was considering in part 2 when we had the discussion about, how you pump up those fermions. So basically, this system maps into that, which means that I can just copy all the results that I had from part 2 into here and see whether this is compatible with data. So we impose constraints. And constraints are, first of all, the potential must be monotonic because the potential is quadratic plus sinusoidal. And so the sinusoidal part should be smaller than the quadratic part. Otherwise, the inflaton would get stuck into local minima. Again, I'm imposing that energies are below the 4 pi f cutoff. I'm imposing that the tensor-to-scalar ratio is in agreement with the observations. There are these other conditions: negligible back reaction, no oscillations in the scalar power spectrum, no non-Gaussianities, getting the right scalar spectral index. These conditions are all automatically satisfied once the top 3 are satisfied. So I have only to satisfy those 3, and everything else is satisfied. And here I have my final result with great timing. I have again a theory with 3 parameters: this lambda hat, that is the amplitude of the instanton-like component, mu, that is the mass of the inflaton, f, that is my f axion, essentially. And again, I can eliminate one of the 3 parameters using normalization of the scalar spectrum with Kobe, or if you want, Planck. So I'm left with 2 parameters. And it turns out that these are this is the parameter space. On the horizontal axis, again, I have the parameter f in units of Planck mass. So you see it's about 10 to 15 GeV or so. On the y-axis, I have mu in units of the Planck mass, so the mass of the inflaton. Above, this gray area is ruled out because it would produce too many gravitational waves. In particular, standard inflation would have mu more or less here, if you see my mouse. And this is ruled out because we don't see those many gravitational waves. This part here, this EFT, this is because this would involve energies that are above 4 pi f, so where my dimension 5 operator is not trustworthy anymore. And this bottom part here is monotonicity, is that the inflaton potential in this region would develop local minima. And so you see there's a white area that is still allowed by data. So in this case, my potential is essentially quadratic. I'm embedding it in a supergravity model with this instanton somehow motivated things. And for free, basically, without doing anything else, I'm getting this fermion production, this new contribution to the scalar spectrum. And effectively, this region is allowed, bringing back quadratic inflation in agreement with observations. So, and perfect timing, luckily, not that I really planned on it. So basically, what I showed here is natural generalization of the quadratic potential to Sugra. With the inclusion of this I wrote it instantons, it's not instantons, is instanton-like contribution, and bring inflation, quadratic inflation in agreement with all existing data. If I go back here, I see that the white area doesn't go down all the way to infinity, which means that there is actually a lower bound on the tensor-to-scalar ratio that I can observe. And we didn't decide anything, it just came naturally, that is 0.004. That is a nice number because it's probable in the next decade or so. This can be generalized to monomial potentials, and well, the last part I didn't really talk, so I will not even mention it. It's some potential work in progress. Thank you.
Well, thank you.
It's a lot of stuff here. I realize.
Thank you, Lorenzo.
Very well. Go ahead. Let's have a discussion.
Yeah.
So
I'm here.
So, Lorenzo, first of all, it's great to see you.
Yeah,
again.
same here.
And
Great to see you.
It's a great talk. I thought you presented all that really
Thank
well.
you.
I'm curious. So I have a very broad question, which is, you motivated at the very beginning, you expressed your love for the quadratic inflation through its simplicity. And this is definitely less simple.
Oh, yeah.
So how do you feel about all that?
I feel that, I mean, quadratic inflation by itself is gone. This is not great, but but my take on all these things is always that unfortunately it becomes a beauty contest. And this is not so beautiful, but what I see out there is also not so beautiful. It's just, to me, let's put it this way. Let me put it this way. let me put it two ways, okay? The thing I like the least of this construction, so let me start with the thing I like the most about this construction. In a sense, is very minimal. I'm saying I'm taking a supersymmetric model, I'm adding instantons, and everything else is an instanton motivated, instanton-like contribution, and everything else comes out for free. Then I add, I'm lying. Because the problem is just to get quadratic inflation to work in the first place. And this is where I'm brought to use all this, stabilizer model, shift symmetry, all this stuff. And that's less beautiful. What can I say?
So let me offer something more in your defense. Maybe quadratic inflation as it was first considered is too simple. Because like, where does it come from and all of that? So maybe you've given some context.
As I said,
where it could, so all these things are supposed to fit together somewhere.
So, I mentioned that flattening thing. That flattening thing is a very natural outcome. Again, it's not obvious. Right. This I will put it the same way. Let me put it this way, in a different way of motivating what I'm talking about. When, Nemanja and I started doing this thing with this quadratic inflation where the inflaton is effectively an axion, one thing we looked at was to put this little superimposed oscillations. We weren't the only ones. There was a big explosion of work on little superimposed oscillations to the potential. Okay? Yeah. What I'm having here is exactly the same thing. I'm just saying, if I put these little superimposed oscillations in a supergravity context, then I'm getting also all this ton of fermions for free.
Cool.
So in this sense, I would argue I didn't invent anything. And this is actually, since I have it still on the last thing, this is the point in the last, in the summing up, in the last point in my slide is precisely, potential work that one day I will do when the pandemic is over, if ever. That is, there were all these papers with these oscillations. What we found is that at least in this specific model, if you put the oscillations, then the fermions, the effect of the production of fermions actually swamps the effect of those oscillations. So how robust are those oscillations if I try to put this in a supergravity model? Of course, you could say always, who cares about the supersymmetry, right? But
Thank you. Yeah.
Long answer.
Yeah. That's good. Yeah, glad to hear it.
Other questions, comments, complaints?
So what you're claiming is that you have a fermionic analog of a curvaton.
Yes, bravo.
You have a curvaton, but it's not a scalar. It's a fermion. You in a certain sense, you're claiming that the curvaton can be a composite of a fermion.
I mean,
which gets into this nice precarious, careful balance between the falling apart and being produced, squeezed. Mm-hmm. And the strange thing about it is that you would have expected that it wouldn't be so stiff. I'm going to call it fermion condensate in the absence of a better word. Sure. Although obviously this is not a condensate like in QCD or something, but in a certain sense, it's like a classical condensate that you built up.
Yeah.
But by the way, just a quick technical. And what happens with Pauli blocking? I mean, obviously you can't crank up the amplitude of the.
Sorry. I mentioned it only in passing. The point is the following. Pauli blocking is always satisfied. So the fermions themselves at long wavelengths are totally irrelevant because occupation number is 1 and energy is small because K is small. But I make up because I'm filling the Fermi sphere to very large energies. So I have a lot of very high energy fermions. And those very high energy fermions interact with each other like crazy, and they produce a lot of average energy inflatons that then are redshifted away and become fluctuations.
Okay, I think I understand. What you're doing is you're saying it doesn't matter that the amplitude isn't that important. It's really delta rho over rho that you want.
Exactly.
So the
Exactly.
amplitude cancels out between those two terms. You just want to make, it turns out the strange thing about your fermion is that the fermionic condensate, again, in the absence of a better word, is stiff so that it produces Gaussian perturbations rather than very non-Gaussian ones.
Okay, yeah.
Right? And then the statement number 2 is that it appears that at the horizon crossing it is roughly independent of K.
Yes.
And you didn't have a you didn't have a reason to expect that, given, you know, the jungle of detail.
Oh yeah. Well,
Let
I
me
mean,
now ask you
please.
regarding the jungle of detail. If you found that basically the spectrum is something like scale invariant at horizon crossing,
Yes.
isn't there some hidden symmetry that in the dynamics that tells you that?
Yeah, I mean, it's just that, you know, I assuming phi dot constant, h constant, so there's a time translation symmetry there, and that's
which is translated into, again, the Sitter symmetry. Okay, all right.
exactly.
So basically,
Yeah.
you're saying it simply follows from the fact that you think that you have an equilibrium which lasts for long enough.
Exactly. And I have to assume that. And I mean, let me say
You
what
know,
I have. What I have to
help you.
assume.
Go on.
I found an equilibrium point. I have to assume that it's a stable equilibrium point.
Sure. Let me help you here.
Okay.
Okay.
I found an equilibrium point at which I am
you don't
producing
even
at the
need
same
to
rate at
assume
which
this.
I am
You
diluting.
only need to satisfy those conditions for the first 10 of the last 60 folds anyway. Because that's what you see in the CMB. If the conditions of your quasi, I think he's froze again.
With one gasp on the way out.
Yeah, I think he froze again. Well, at least we had the talk, so that's kind of good.
Yeah.
I'll contact him via Skype to see if he will be able to return quickly. Otherwise, I think he's rebooting his Zoom or whatever is going on.